coefficients.
Oh, thank you very much, Marta, and I thank all the organizers for inviting me in this lovely place again. So my talk will be on Morse theory with differential grade coefficients. So it's joint work with Barreau, Imilière, and Wancha, whose first part is already on arXiv, and the second part will be probably on arXiv quite soon. So the plan is, so it's about Morse theory, so I should start with some basics on Morse theory. Maybe some students are back, so it could be useful for them. And then I'll try to fit a little bit into the topic with some symplectic motivation. And third, I will give the definition of this Morse theory with differential grade coefficient, and I'll finish with some application. So that's the plan. Let's see what I'm able to do of it. So basics. So now Morse theory, you probably know this. Let's start with some closed manifold. And then this is a Morse function, meaning that all the critical points are non-degenerate, and then negative generic gradient, which means that df psi is less or equal to 0 with equality in the critical points. And the generic means that the unstable and the stable manifolds are transverse. And with this data, one defines the Morse complex defined like this. So Ck of f is Z spanned by the critical points of Morse index equal to k. And then the differential of x is the sum index of x is index of y equals index of x minus 1 of the number of trajectories going from x to y times y. So we count these trajectories between critical points of consecutive indices to define our complex. And the fact is that first it is a complex, and then it has the property of invariance. Invariance means independence of this Morse couple, f psi. And so we may define the homology of it, and the homology of this complex is actually, as probably everyone knows, the singular homology of x. And the reason why it is like that is that these unstable manifolds form a CW decomposition of x. So somehow the general idea of the talk is to get more information from this Morse data. Because after all, since this Morse data provides a CW decomposition, in principle, it knows everything about the geometry of the manifold. And what we do when we do Morse theory, we just use a small amount of this information by only taking the trajectories between consecutive points of consecutive indices and having some particular count of these trajectories, right? I forgot to say the reason why it can be counted is that this space of trajectories is the transverse intersection of these two manifolds divided by R, so its dimension is, this is well known. So following this idea, the first step could be to do one more clever count of this number. And if you do one does one more, this count, one may get the homology with local coefficient. And this goes like this. So take the universal cover. And for every critical point x, in x, consider the fiber. So this is pi minus 1 of x. And define this complex xi, which is spanned now by all the fiber, where x is a critical point with index k. And as a differential, so taking one element of the fiber here, and then one element of the fiber there. So it's the sum with index of y equal of index of x minus 1 of the number of what I denote like x, Lx tilde y tilde. And Lx tilde y tilde is simply the subspace of Lxy formed by all the trajectories which lift exactly between x tilde and y tilde. This is again finite. And one can prove again that we have, it's an easy exercise. D squared equals 0 plus invariance. And what you get is a homology of this complex, which is actually the singular homology of the universal cover. Again, a reason for this is that the preimages of W provide a CW decomposition of X. Okay. So actually, one may think of this kind of infinite dimensional complex in a slightly different way by fixing a lift in every fiber. And then this fiber can be written actually like this, pi 1 of x. It's all the multiple of x hat by the element of pi 1. And therefore, our complex now can be written like that. So it's now a finite dimensional complex over z pi 1 of x, but now it's spanned by these fixed lifts. And so the differential here, the differential is x hat is some y index of y equal of index of x minus 1 of the number of L x hat G y hat times G y hat. So this is something that belongs to. So this is just another way to see the same thing. And now, more generally, one can now consider a module over Z pi 1 of x and form this complex x, f, xi, m, which is m tensor with the preceding one. And so we have, as before, d squared equal to 0 plus invariance. And what we get is the homology of it. It is what it's called homology of x, n, so homology with local. For instance, one example of it, if you take M as a Novikov ring, what you get is what is called Novikov homology. So that's an example. Okay. So now the goal is to replace this M by a complex. So this is where the word graded comes from. Such that it will be generalized, the case of local coefficients. The case of local coefficients will correspond to this complex. Okay, so that's the goal of this Morse theory with the G coefficient. Okay. So this being said, I'm ready to write something about the motivation part. Motivation. And so motivation is, as I said, of symplectic nature. So let me start with the symplectic manifold. And take a Hamiltonian, which is a proper function. And there is what is called Hamiltonian-Seifert conjecture. Stating that for every regular level C, H minus 1 of C carries a closed characteristic. So to my knowledge, this was disproved for the very first time by Victor Ginzburg and Michel Herman. So the answer is no in W equal to R to N. And so this is not true, but what it is true is what is called almost existence. So I note like that. So this says the following: for W equal to R to N, for almost all C regular level, regular value, I would say, there is a closed characteristic. And this was proved by Hofer, Zehnder, and actually their arguments was kind of enhanced by Struve. So there's a lot of literature around this topic. So some of the authors are in this very room, so including like Victor and Bashak-Gurel and Leonardo, Macarini. And what I will talk about is something related, quite close to this topic, which is the following. So in our framework, let's start with the compact Liouville. Manifold, which will be supposed orientable. Actually, very soon, I will turn to the easy case of, easy? The case of the unit cotangent bundle of the compact manifold. But for now, let's take this general case. And I will give the following definition. So let sigma be the boundary of some u. U is a domain in W. And sigma is a preimage of a regular level. Okay? So this is, again, a kind of a classical definition in this topic. So I will say that sigma has the almost existence property, and I will add a 0 here, if there is some epsilon such that for almost every d in C minus epsilon, C plus epsilon, H minus 1 of d has a closed contractible characteristics. So the 0 there comes from the contractible thing. Okay. So we are interested in this almost existence property for contractible characteristics, and we have a criterion about that, which I will write down. So this criterion is adapted from some recent work of Irie. And it says like this. So first, it involves symplectic homology of the manifold. And this canonical morphism between the zero energy, which is called SH0 of the symplectic homology, to the symplectic homology. Now, I won't define symplectic homology, but actually, very soon we'll turn on to a case where we know what this morphism is and what the symplectic homology is, so it won't be quite necessary to know what it is in order to follow the sequel. Now, our criterion is the following. Let J be the inclusion. And suppose that there is some alpha in here such that first so this morphism sends alpha to 0 in the symplectic homology. And second, and the J shriek of alpha, which lives here, this is not 0. Now, I probably say something about this. So the J shriek is simply J shriek is the Poincare dual of the cohomology application induced by J, which goes from this to this. Okay. So if these two conditions are fulfilled, then sigma sigma is the boundary of U, right? Has this okay. Maybe I should have noted here that, for instance, the answer is no if, let's say, sigma is the, if U is the entire unit cotangent bundle of the torus, let's say. There is no contractible geodesic, okay? So that's our criterion. There is some, yeah. So let me make a remark here. So if this homology is 0, then the criterion is satisfied already for the fundamental class of W. Since, by definition, this shriek map sends fundamental class into fundamental class. So it means that G shriek of the fundamental class is not 0, okay? So this was actually the case of Henrique in his criterion. Okay, so secondly, I will write this criterion in a very short manner, like this. So the kernel should not be included in the kernel. That's the criterion. Okay. And now I will turn on to this to the case of the unit cotangent bundle. So let now W be this manifold. And when is this manifold? There is the celebrated Viterbo isomorphism, which says that the symplectic homology of is actually the homology of LQ, and this is the free loop space. So in order to write our criterion in this setting, we have to say what this morphism is in this case. And actually, this is known too. So if we write this, so we have this plus n here, this morphism. So this can be written like this. Okay, so this morphism, no, via Viterbo, we are here. And then here we have a Thom isomorphism. And actually, it's known that this diagram here actually commutes, where I here is just the inclusion of the constant loops. Okay? And the isomorphism here is given actually by the shriek of the projection. Okay? So when we compose this criterion with this relation, with this isomorphism, we just may write this criterion using this application here. So here we have, on this side, we get I star. And on this side, we get the composition of J shriek, P shriek. So the shriek is contravariant. So this is P composed J, P composed J shriek. And this is just the projection of U on the base. Right? So we have this. Now our criterion is this one. So this is very nice, but actually, as written, is kind of useless, because obviously I star here I star is injective. So this criterion is never fulfilled in this setting. And it's injective because you have you can write this evaluation just evaluating a loop in its initial point, and you get here by definition you have that, and then you can put a star here, and then that's it. I star is injective. But remember what I told you at the beginning. The idea is to change the coefficients. So question, what if we change the coefficient? Let's try as a start to see what happens when we take local coefficients. Local coefficients, so trying to write this down with local coefficients means the following thing. So take M Z pi 1 of Q module, as it was stated in the introduction, and then write the pullback of M, meaning M as a Z pi 1 of LQ module. So M is always also Z pi 1 of LQ module via the evaluation. And then when you write this composition down with local coefficient, we get the following thing. So it arrives here in M. It comes from I'll write it. It comes from and here it comes again from Q. So here I should write this thing, and this is M. So here you have I star, here you have evaluation star, and indeed it's true but that, again, so it's again injective. But one may remark here that it is injective for this very particular choice of the local system here. If it's injective, if the local system here is a pullback of a local system here. But we have the freedom to choose actually any other local system here. And it turns out that there are some local systems for which we can satisfy it. We can have this criterion satisfied. And actually, there is a paper by Albers, Frauenfelder-Wancha, showing that with this criterion that if, let's say, pi 1 of Q is 0, pi 2 of Q is not 0, then every sigma equal, so every boundary of some such domain has the almost existence property for contractible. Actually, what they show is something more general, which is that the Hofer-Zehnder pi 1 sensitive capacity is finite of the unitary cotangent quantum. So now I arrive to our construction. So what we want to do in this setting is, what if now we take DG coefficients? And this I'm going to explain the construction now. So our idea was somehow to use all the trajectory spaces, okay? So we want to use all LXY for arbitrary critical points x and y. And actually what we do here, we generalize a construction called enriched homology, which is due to Batoreo in cornea. And it goes like this. So actually, we want to use not this Lxy, but rather its compactified space, which is a Lxy union so all the broken orbits.
What's the word before homology?
What's the word for?
Before homology. It's what homology?
They call this enriched. Enriched.
Okay.
So this is their word for that. So these are all orbits from X to Y, which with some stops. And this is of codimension K in so we want to use this space. So the first feature of this space, which is useful, is that it has a structure. And the structure is that of the it's a manifold with the boundary and corners of dimension so I learned this proposition from Latour. Laudenbach had the proof too, and I don't know who proved it the first. So it has this structure. And in particular, what we want to use from it is the fundamental class. And this fundamental class, we will see it as a chain, cubical chain, in the complex, cubical singular complex of L bar xy. Now, the cubical complex is just the same as the simplicial complex, but simplices are replaced by cubes. Like this. And actually, we have to quotient by some degenerate cubes in order to have the homology of the point equal to the isomorphic to the homology, usual homology of the point. So the degenerate cubes are the ones which factor with some projection. So this is just a small technical issue. It will be clear in a moment why we use cubes rather than simplices. So we want this to use this fundamental class And actually, so we want to write down a relation involving this fundamental class. So when we take delta of this fundamental class, we get the fundamental class of the boundary. And the boundary one can write it like this. It's the union of okay. So it's kind of a union of some, can see that as some rectangles. It's not a disjoint union, but the interiors of these rectangles are disjoint. So if one thinks that the fundamental class heuristically as the sum of the cubes of top dimension, what one wants to get out of here is this kind of relation. Okay. And actually, this is a proposition by Batoreo and Cornea saying that one can choose such a SXY in the cubical chain complex of LXY such that, so X, there is some SXY such that, donc representing fundamental class, such that we have this, and actually you have this is sign here. So this is the relation we wanted to use out from the structure we had on this L bar. And secondly, we want to use an evaluation into the, yeah. It's quite hard to complete. I mean, it's quite hard to complete. How to say a cellular decomposition in this way. So this is not. It's not the way they did it. Actually, the proof is more of an inductive process. I can maybe show you later, but it's. Using cellular decomposition makes things quite harder in this topic. And the evaluation goes like this. So start with a broken orbit, transform it in some path. So actually what it is, it's a path from x to y in x, parametrized by the value of the function. Okay, so take this path, the parameterized path, and then use a tree. So you take a base point and define a tree with branches connecting the base point with all the critical points. So this is the tree. And we collapse x on this tree, and so we land in this space. Sorry. Okay, have a loop in this collapsed space. And then go back in the loop space by taking a homotopy inverse. So now we have this evaluation, and it satisfies. So all this, so it starts from here, and it's called QXY. And it satisfies the following. If we evaluate, like this is lambda, and this is lambda prime, and we take this evaluation, and it goes to some intermediate points, z, then actually this evaluation is like concatenating the first one with the second one. So this is B. Okay, so we have this thing coming from the structure, this thing coming from the evaluation, and then what we get out of this is the following thing. So it's natural to set mxy equaled evaluation of this fundamental class. So this lives in the singular cubical chains over the loop space, of the Bayes loop space. Okay. And A plus B implies the following relation. The differential of this mxy here equals this relation. Okay, and the product here, this is what is called Pontryagin product. But actually, with cubical singular homology, it's very easy to define what is the Pontryagin product. So take a cube here, and the cube there, and we apply it to the variables. This is in 0, 1 k. This is in 0, 1 l, and actually you have sigma of z concatenation of tau of z prime. So this is the product. Very natural. So we finally got this equation, which is an equation of type Maurer-Cartan. And this is known to be used to perturb differentials. And this is what we're going to do. So now we are in position to define our complex. So it depends on a extended Morse data. So we have the Morse function. We have the gradient. We have some orientation of the unstable manifolds, as in the classical Morse case. We have the choice of this x as xy. We have the tree. And we have this homotopy inverse theta. Okay? And so we define this complex. And now we also add here these coefficients, the DG coefficients. So F here is a DG module over meaning that we have Fk Cl goes into Fk plus L. This is a module structure. And of course, it's a differentially graded module, so we have plus Leibniz rule. Okay. So this is our complex. And the differential, so I didn't define it, so let me define it. Ck of F is the sum of Fj times tensorial product over Z of Ci of F. So this is just a usual Morse complex spanned by the critical points. Okay, and here, and then the differential works like this. Differential alpha times x is differential alpha times x plus -1 degree of alpha sum alpha times mxy times y. And here y is a critical point, any critical point of any index. Okay. And what we get from here is proposition. So actually this Maurer-Cartan relation implies easily that d square is 0, and maybe less easy to prove that the homology of it is invariant with respect to all this huge Morse-like data we chose. So we get the homology. Now, question, what does it compute? Define a huge thing. What does it compute? Computation. So, two examples. First, for this complex, now here M is a Z pi 1 of X module, okay, as in the local coefficients. But being a Z pi 1 of X module, actually, if we remark that the H0 of omega x is actually Z pi 1 of x, okay, it is also a C0 omega x module. Just by the projection of C0 to H0. So actually this thing here is a DG module over the C star omega x. And as expected, what we find here is that the homology of X with DG coefficients in M tilde is the homology with local coefficients. So this was kind of a baby case since the beginning. No, more general than that. Take a Hurewicz vibration. When you have a Hurewicz vibration, you have naturally that omega x acts on F, and this gives rise to DG model structure of the singular homology of the fiber over the singular homology of the loop space, right? So we can consider this F, and when we compute, what we find is the singular homology of the total space. So this is kind of an independent interest. It just gives a Morse description of the homology of the total space of any Hurewicz vibration. Okay. And now, in like last 3 minutes, I try to give an application. Let me give maybe just an example here. If you take F, just the complex, singular complex over the based loops, this is a DG module with Pontryagin product. And what we get from this is that, so this corresponds to this vibration, which is called the path loop vibration. Okay, so the total space is formed of paths starting from the base point and going somewhere in X. And therefore, what we've got is that the homology of X with coefficient here is the homology of the path space. So it's homology of the point. Okay. So this was actually the case originally considered by Barreau and Cornea. And now let me state an application. So proposition. We take Qn orientable, not K pi 1. And you take U into this unit cotangent bundle. And then you take another manifold, let's say L, such that L admits a smooth, even continuous application into U, such that phi, so PU phi, which goes from L to Q, is of degree 1. So suppose there is such an application phi. Then sigma, which has the almost existence property for contractible. So this kind of generalizes the case where this phi is a Lagrangian embedding. It's known that if an exact Lagrangian embedding, it's known that an exact Lagrangian projects onto the base with degree 1, and it's known also if some domain just contains an exact Lagrangian embedding, then it has this almost existence property for contractible. Okay, but let me emphasize, this is a condition of differential nature. It's not symplectic. This condition is purely differential. So I'm 2 minutes over time. May I have some 3 minutes just to explain the broad idea? Okay. So the idea, so use the criterion. But the criterion for DG coefficient this time. So in the criterion there, we have this application, I star, so here it's I star of f. And this is the free loop space. Now we pretend here that the free loop space is a manifold, actually, but I mean, you have to adapt all this Morse construction in the case of free loop space, which is the manifold, but let's skip this consideration. So here, what we are going to take the loops, the base loops over the free loops. And when you take the base loops over the free loops, considering what I told you there, what we get here is the homology of the paths in the free loops. And this one is the homology of the point, as said before. So the homology with integral coefficient of this space is huge. But when we take this specific DG complex, it becomes the homology of the point. Okay? So we have, it's formed by paths like this. Whereas this homology turns out to be the homology of the pullback vibration of this inclusion. So actually, it turns out to be the homology of the pointed spheres. It's just like these paths, but which close into points. And this inclusion comes from this inclusion, the spheres into these cones. These cones have trivial homology. These spheres on another, the spheres, so the homology of this space of pointed spheres is the homology of the point if and only if Q is a k pi 1. So if Q is not a k pi 1, the homology of this space is quite huge. The homology of this one is quite small. And actually, we find a lot of things in this kernel. And this condition is used to prove that using this condition. So probably stop here. I could give some more details, but I think it's time to stop. Probably.
So any questions?